sit down with me.
And you're gonna be mad.
Yeah, they
Okay, we're starting.
that they're gonna take all my money, and I'm like, no.
Wow.
We're continuing with 2.2. Pretty much one more thing I want to cover from this, that's continuity. So, let's talk about what this intuitively is, and then we'll make it more precise a little bit later. So essentially, you kind of say your function is continuous in some region. If you can kind of sketch it without lifting your pencil off the page in that region. So it kind of means that the function has no gaps, no holes. It's not fragmented. That there's nothing wrong with being able to draw this function. So, for example, you can think of a function as being continuous on an interval a, b. If you can just kind of like draw it in a, b without lifting your pencil off the page, you can just continue, everything flows nicely. Whereas something that's not continuous, you can't actually do that. So something that's not continuous, you might have something like a jump. Or you might have something where at a single point it's undefined on that region, so you have to lift your pencil off the page to avoid that hole. You could find it where it's defined everywhere, but at one point it's defined strangely compared to all the other points. You could have things like, for example, asymptotes. Right, where you have to draw the two sides separately. So there are many cases in which something can actually break. But in the case where something doesn't break, you can actually just draw it without lifting your pencil off the page. We call that function continuous. Right? And that's the property of continuity. Now this guy is actually important because calculus will only work where a function is continuous. So knowing when this happens is in general important. And so let's actually talk about how we can determine whether something is continuous or not. We can use limits to determine continuity, it turns out. Kind of leads us to the first definition in this segment, 2.2. Function f of x is said to be continuous at a point x equals a. If this equation holds, the limit as x approaches a of f of x is actually equal to f of a. Well, of course, he denoted that the limit exists. So I think that was actually also a bonus. One of the parts of the bonus for the first test were actually to define using an equation when a function is continuous at a point. This would be the equation. So we can talk about a function being continuous at a point, x equals a, if this equation holds. And of course I want to bring to your attention that there are three things that kind of need to happen for this to hold. And that's the following. One, notice that f of x must be defined at a. Meaning f of a must exist, it must be a number, it must make sense in our function, it must be something that I can actually write down a number for. So there's no like hole at that point. The function will have something filled in. The second thing is that the limit must exist. Right? Which, by the way, you can oftentimes break that down into two other things. Where you talk about the left and right must exist. Limit as you're approaching from the left, and limit as you're approaching from the right must exist and be equal. The third thing that needs to happen is that these two values, whatever values that you get from them, they must agree. 1 must be equal to 2. So there are three things that need to happen. We have to be able to find the limit and get an answer. We have to be able to evaluate the function at the point and get an answer. And thirdly, these two answers must agree. Whenever that happens, it turns out that our function will be continuous at that point, and we can actually draw the sketch of our function passing through that point without lifting our pencil off the page. So that when these three things are fulfilled, that criteria will always be met. You'll always be able to sketch the function without doing anything too crazy. Some functions can be crazy, actually. Let's just do like a big example here. So I'm going to give you sort of a pictorial example, but the idea is that you want to be able to do this kind of analysis without actually seeing a picture. Just by checking the numbers as I'm going to check them. So let's look at an example here. So this is my x-axis, this is my y-axis. Let's put some numbers in here. So let's say this is like at minus 10, minus 8, minus 6, this is minus 3, this is 2, this is 3, this is 4, this number here is 1, this number here is 2. So there's a picture of a function, and in general I didn't have to give you a picture. I could have given you this as a piecewise defined function, where I tell you about what's it defined as in the pieces. And if you could sketch it in theory, you would have sketched it and gotten something like this. But we're really going to focus on the numbers here. Because I want you to see how we can examine a function based on the numbers. So from this though, we can actually point to the parts where the function is not continuous, right? Intuitively speaking. Like what x values are we not continuous at? -8? Yeah, so if I'm drawing here, I'd have to lift my pencil up, fill in this point, cut back here and draw it. So if I'm around the region 8, yes, I have to lift my pencil off the page in order to sketch that, so that's not continuous anywhere else. Yeah?
2 and 3. That area is the
Yeah, because here if I have to lift my pencil up to avoid 2 and I have to make this jump to get to 3. So here we expect it to not be continuous. Where else?
-10.
-10 because there's a gap here.
-3.
-3 because there's an asymptote. So I literally have to draw these two parts separately. Okay, so you can tell from a picture, right? 4 technically is also going to be bad because I can't really draw through that point. But we'll talk about that in a little bit. So here's how you'd examine each part. Let's say we're talking about an x equals -10. And I want to talk about whether my function is continuous at that point. I can clearly see that it's not, but let's see how the numbers can tell us. What you can look at is the limit as x approaches -10 from the left of your function. Limit as x approaches -10 from the right of your function. Limit as x approaches -10 of your function. And what is the value of your function at x equals -10? So we can look at all these numbers. So what is this guy here? It's 1. From the right, it's also 1. Which means if those two agree that our limit must also be 1, what is the value of the function at the point? Does not exist, it's undefined. So because these two do not match up, in fact this one does not exist, I can say it's not continuous here. Right? So let's say even if you didn't give the picture, but you can actually find these limits because I gave you a formula, and you know how to find them from the formula. You can figure it out that that was not continuous. What about at x equals 8, -8? You can again go through this process of finding the limit from the left, finding the limit from the right, finding the overall limit, looking at the value of the function. So similarly here, if I'm finding the limit as I approach the -8 from the left, the answer is 2. Approach -8 from the right, the answer is also 2, so the limit is 2. But the value of my function is 1. So we're not in a case where something is undefined. That actually is defined. But because it's not, the values aren't equal, one gives me the output 2, the other gives me the output 1. Again, it's not continuous. You can look at the point where x equals -6. Take the limit as you approach -6 from the left of your function, you would get 1. Take the limit as x approaches -6 from the right of your function, you would also get 1. Which means that the limit as you approach -6 of your function is 1. If you look at f of -6, that output is also 1. So all these numbers actually line up, 1, 1, 1, 1, 1. They're all equal. They all exist and they're equal. And so here it is continuous. So we can kind of go through and do this for all these points. You'll notice that -3 is not continuous since your limit as you're approaching -3 of your function does not equal the value of your function. In fact, this guy here is undefined, while this guy here is giving you -infinity, right? And you can talk about, for example, at x equals 2, you realize that the limit as you're approaching 2 from the right does not exist, which means that the limit does not exist. So it's not continuous. Because if the limit doesn't exist, there's no way I can set it equal to some number. Right? It's also true that f of 2 is undefined. But once you determine that the limit doesn't exist, it doesn't even matter. X equals 3, a similar reasoning. The left-hand limit does not exist. So it's not continuous. For 4, the right-hand limit does not exist. So again, that's also not continuous. So we can actually use limits and talk about the value of a function, and we can use those two pieces of information to define when a function is continuous. When can you write it without lifting your pencil off the page? In terms of something like 3, there is such a thing as one-sided continuity, but it's not something we're going to worry about in this class. We're just talking about continuous in general. Okay? But the numbers have to match up in order for that to work out. So that's the takeaway here. The limit must be equal to the value of the function at the point. Is there a calculus 2 that you guys have to do that goes with 12 with 3?
Depends on the major.
Depends on the major.
Okay. Because I couldn't say more, but I think that's good enough for our purposes. So that's all I wanted to say about continuity. I just want to actually, some questions that were brought up in my other class, and I just want to see if you guys will know how to handle them. Let's say you wanted to find this guy, how would you do it? Limit as x approaches 0. That guy. Maybe also limit as x approaches 0. That guy. Yep.
It's tedious, but you can put in values that are really close to 0 and then solve for it.
Yeah, you could do that. So yeah, so we know our limit strategy. The first thing we want to try to do is to actually plug in that number, but we can't because we divide by 0 if we do that. But we don't really jump to that whole idea of plugging in numbers right away, even though technically we could. We could plug in numbers like 0.1, 0.01, 0.001, 0.0001, and get close to 0 from either side and keep checking the y values. But let's say this was on a test, you don't have that time. I mean, even in theory, if you calculators are allowed and you can actually use your calculator, that would still take you a pretty long time to actually track those values down and come up with a table. So there's actually an easier way. There's a way to simplify this that we have seen before in this semester. How would you simplify something like that? Ideas, you see something like that. How would you simplify it? Yeah?
I'm thinking like you can make the x, like you could say the square root of 4 plus x minus 2 times x and make it 1.
Okay, but how would that help you though? So I just bring this up and write it as all of this times x to the minus 1?
Yes.
Like, how does that make it easier? Like, what could you do after that that you can't do now? Yeah?
Would you multiply by the conjugate?
Well, that's something we have done before, so let's see how that works out. Let's try multiplying by the conjugate. So I have a sum of terms in the numerator where one of them has a radical. That's probably getting in the way of simplifying because I know if that radical wasn't there, it would be easier to simplify. So let's try to get rid of the radical by multiplying and dividing by the conjugate. Which means they're multiplied by the same expression except the middle sign is changed. So the numerator, I would have to multiply these two things. Now what you would notice here is that this is like a minus b times a plus b. So I know that that becomes a squared minus b squared. So it's going to be this squared, which allows me to get rid of the radical, minus this squared. And that's the entire numerator. In the denominator, I'm just going to have x times this guy. Now what can happen?
9.0.
Well, I can't. There's still an x here. Now what can I do? Yeah?
Do you do 4 minus 2 squared? You can't
Yeah, in the
cancel
top,
out.
2 squared is 4 in fact, so this is like 4 minus 4, so that would go away.
And then you can cancel out the x over x.
And so this is going to be x over x times this guy, 4 plus x. And so, yeah, now I'm allowed to cancel that x. So this gives me the limit as x approaches 0 of, now this becomes 1 over radical of 4 plus x plus 2. And now I can plug in x equals 0 because the denominator won't be 0 in that case. Plug in x equals 0 here, I just get radical of 4, which is 2. Add 2, I get 4, so this just becomes a quarter. So that limit is a quarter. And yes, you could plug in numbers closer and closer to 0, and you'll see that all the numbers are getting closer and closer to 0.25. But that would be a lot more tedious than if you saw this method. You get to the exact answer pretty quickly. What about something like this one? So this is a complex fraction. So we kind of know how to deal with those. We want to multiply and divide by the LCD. The denominator of that 1 is 1, the denominator of x in the denominator is 1, so the LCD ends up being x plus 1. So I'm going to multiply and divide by x plus 1. So I'm going to take that guy, distribute, multiply each of those. X plus 1 times 1 over x plus 1, the x plus 1's cancelled, minus this times 1, put that guy in parentheses, because that's going to be important, and the denominator is that. Now we can again simplify this 1 minus 1, so that goes away, and so I have negative x in the top, x over x plus 1 in the bottom. X's can cancel. So I have the limit as x approaches 0 of minus 1 over x plus 1. And now I can plug in x equals 0. So minus 1 is the answer. But that ends this section. I just wanted to show you guys that sometimes the limits, you have to do some sophisticated kind of simplification on these, but you should be able to do that. That might come in handy with some of the homework problems as well. So we're officially done with 2.2. So the homework for that is due The next time I see you guys, which is actually not Tuesday, hopefully you guys remember that. Monday, it's President's Day and the college is closed, and so on Tuesday they have a Monday schedule. So Tuesday coming next week, we don't have class. It will be like a Monday. So whatever your classes are on Monday, that's what you'll have on Tuesday. And so the next time I'll see you is next Friday. And at that point, we'll be continuing something we're going to start right now, which is a very important topic. This is kind of going to be a very pivotal point in our class. We're officially kind of transitioning from very algebraic things to things that we're going to actually be using calculus. So this is section 2.3, but I'm kind of going to do it in conjunction with 2.4, kind of get, because the ideas are very closely together. I'm going to do them at the same time. And it's called the derivative. And its applications. Now applications we'll be doing a lot of as we move on in the semester throughout even future sections, but we're just going to mention a few of its applications here. And that's what we're going to talk about now. So I did mention before, that if you wanted to know what calculus is a study of, limits would be the one-word answer, but a more expanded answer would be it's the study of derivatives, integrals, and their applications, right? So today we're going to talk about one of those guys called the derivative. And what the derivative is, it is the solution to the so-called rate problem. So there are two major problems. I mean, mankind had many more problems, but there were two that were really bothering us back in the day that we really need to be able to solve. One was called the rate problem. So that was the problem of figuring out the rate of change of certain quantities. So if you look around in life, you realize that everything changes. Populations grow, sometimes they die out. You know, if you're planting crops, sometimes they grow, sometimes it dies out. Things break down over time. Things are constantly changing. Things are constantly in flux. And we kind of wanted a way to know how fast this change is happening and what that would mean in the future if we want to make plan for the future, for example. And so this idea of taking something, there are some times when we can actually predict the growth of something. If, for example, if we had a linear model or an exponential model, we know that if it's increasing by a fixed amount per unit time, okay, we can use the equation of a straight line, that's fine. If it's increasing by a fixed percentage amount per unit time, cool. We can use an exponential equation. But what if it's the pattern by which something is growing or decreasing is kind of haphazard, and it's not really something that we can get a handle on how to describe it. How can we figure out how fast it's moving at that point? And the answer to that would be to actually develop something called the derivative. So it's a very useful mathematical machinery that you can put on top of a function that's doing something crazy, and out of that you can extrapolate how fast the function is moving and what's its rate of change and things of that sort. And so that's what the derivative is about. It was the solution to the rate problem, to figure out how fast something is moving. Another problem that we were very concerned about was this so-called area problem. And this was the problem of figuring out how much space something takes up. So if you're looking at something like a rectangle, right, figuring out the area of that's no problem. But if you're a farmer and you owned a plot of land that had this weird shape around it, how much land do you actually own? You know, as an example, right? So if you wanted to plant a certain number of crops, you wanted to know how much space you have, or you know, you want to know if the government isn't charging you too much property taxes because they claim you own more land than you actually own. This is something you want to know. You want to be able to measure this random shape, like how much space that takes up. And that's kind of where integral calculus, or the integral, comes in. It was a measurement of figuring out space. So these were these two problems, figuring out the rate problem, how fast something is changing, and the area problem, how much space something takes up. And these are problems that we have had tools of dealing with before. I mean, way back in like the the 200s BC, Archimedes was already solving problems using things akin to integration that we know today. And he was figuring out the area of all sorts of weird shapes. So we have kind of been using these tools in these separate spheres, but then Newton and a guy independently called Leibniz came along, and they sort of figured out that these two problems actually had a very deep connection. They're actually two sides of the same coin. Figuring out how fast something is moving is actually inextricably linked to how much space something takes up. And that developed a new theory of calculus that they developed the fundamental theorem of calculus. And that's why now you kind of think of Newton as the father of calculus, even though technically we've been doing calculus thousands of years before him. But he was the first guy to kind of unify this theory of these two things that were being studied separately. We're now studying it as one big thing called calculus. And so that one big thing is kind of comprised of two parts. The differential calculus, which deals with the derivative and its applications, and that's about solving the problem of figuring out how fast something is moving. And then there's the integral calculus, which we use the integral, and that figures out how much space something takes up. And it turns out that one is kind of the reverse of the other. And that's what the fundamental theorem of calculus tells us. And that's something that we'll get towards the end of the semester, but for now we're going to look at the first problem. Figure out how fast something is moving. And we're going to take the typical math approach here. We're going to use the fact that we know how to solve this problem in a very simple case, and then we're going to kind of tweak that to deal with a more complicated case. Okay? So you might have imagined, I mean, you did it in geometry, for example, when you were talking about the area of a rectangle, and you knew how to find the area of a rectangle, so you could actually use that to figure out what's the area of a parallelogram. And then you can actually realize that a parallelogram was just two triangles being stuck together. So you can use that to figure out the area of a triangle. And so now when you get to something, a shape that's not like any of these, it doesn't have any straight lines, you get to something like a circle. And so how do we figure out the area of a circle? Well, what we kind of did was we dissected it into a bunch of triangles, right? We use the fact that we know how to find the area of a triangle to add up the areas of all those triangles, and we reorganize all these triangles in a big parallelogram, and then we use the formula for the area of a parallelogram, and then you realize that pi r squared suddenly popped up, right? So we're going to kind of do the same thing today. We're going to use the fact that we know how to deal with a very simple case to deal with a very complicated case. We actually know, so our goal here is to find the rate of change. And we want to do that in a context that we haven't really been able to do it before. We want to be able to do so, as the phrase would say, instantaneously. So there is a rate of change that we already know about. That's called the average rate of change. It tells you how something is changing over some large interval of time. We want to actually get away from that because for us to be able to do that, we actually have to have these 2 points in time and be able to measure our functions at those 2 points in time. And so we can really talk about what's going on in hindsight. Like I have to pass a huge chunk of time in order to make that measurement. But what if I'm already at the first point here and I want to know how fast I'm moving at that instant? At this point, right now, how fast are things changing? This is called instantaneous rate of change, the rate of change at a single point, where I don't want to go over the whole interval. I want to know at a single point, how fast are we moving right now? Okay, so that's the goal. We don't immediately know how to attack this problem, so we're going to use the fact that we know how to attack simpler problems. We know, for example, about how to find the average rate of change. So that's a start. I know how to talk about change on some interval. Let's see if we can tweak it by making that interval smaller. That's going to be our idea. The second thing is we kind of also know a measurement for the rate of change. So this is back when we were doing the equation of straight lines, and we spoke about the slope, and I told you that here's an interesting interpretation that we'll put on the slope. we look at the slope as a speed of some sort, how fast the output variable is changing in relations to the input variable. And so we also know that slope can be used as a measure of rate of change. So we know how to measure rate of change on average. We also know that the slope is actually a pretty sophisticated tool for determining rate of change. So the idea is, let's put these together. To find instant rate of change. That's going to be our idea. We're going to use these two ideas, we're going to kind of put them together in such a way that we can get to what we want, which is instantaneous rate of change. So let's say I have some function that's doing its thing. There's a point here that I care about at the point x. I want to know how fast is the function moving at that point. What is its speed? What is its rate of change? Right? Because I know the slope of a straight line, right, just for emphasis here, the slope of a straight line can use to measure. What I can do is, what if there was a way to be able to draw a straight line that passes through that point in such a way that if I zoom in, the function and the line are super close to each other, to the point where that straight line is kind of doing exactly the same thing the function is doing. The more I zoom in, the flatter the function seems to flatten out, and it becomes the straight line. And so the idea is, by actually measuring that straight line and measuring the slope of that line, I'd be able to actually measure the slope of the function itself, because that line is approximating that function in that point. Such a line that we can draw through a single point to approximate the function is called a tangent line. And the idea is the tangent line approximates the function. And it has the benefit of being a straight line, which we know everything about straight lines at this point. We know how to find their equations, we know how to find their slope, we know how to interpret their slope. We know everything about this, a straight line. We might not know everything about this random function that we just drew, or something that we were retracting. And so here's the idea of how we can get to that tangent line. You pick another point in the future. Let's say it's a point x plus h. You can connect those 2 points with a line as well. That's finding the average rate of change, and that we also know how to do. By the way, such a line that connects to 2 points in a function, that also has a name. It's called a secant line. So we pick another point that's a distance of h units away. We can draw a straight line through those 2 points. That creates what's called a secant line. And here's how we're going to get to the tangent line. I'm going to keep this point fixed that I care about. And this other point, what I'm going to do is I'm going to push it towards that point. In other words, I'm going to make the distance h get smaller and smaller and smaller so that this point gets pushed into that point. And the closer that I get pushed into this point, eventually I get to the point where these 2 points are right beside each other, and drawing a line through those 2 points is like drawing a line through 1 point. And you can see a progression here, like if you were to draw it out, of all these lines like starting to closely resemble a tangent line. So the idea is we start out with the secant line, and what we do is we fix the point that we care about and push the other point closer, to the point where those 2 points are now right beside each other. And so drawing the line through 2 points is like drawing a line through 1 point, and I end up with this situation. So in other words, closing the gap between the 2 points turns the secant line into a tangent line. And the tangent line is important because it is a straight line that is approximating our function in a certain region. And so I can tell information about my function by talking about information about the tangent line. So now the question is there a tool or some sort of mechanism by which we can actually do this? Is there some way to actually take some distance and inch it closer and closer and closer to zero? We can actually move something and make it approach super close to something else. Do you have something that can do that? Yeah?
Limit.
The limit. That's exactly what the limit was about. So we were talking about limits before, and I told you that we never actually cared about being somewhere. What we cared about is getting close to somewhere. And one of the reasons why this is very useful to us is because of something like this idea. We want to take this idea of closeness to be able to, instead of thinking of something as 2 points, to think of it as a single point. So we can actually close this gap using limits, and that's where the limits come in. And so that gives us the following. This means if I were to take the slope of the secant line, let's actually measure that here. Let me redraw this down here a little nicer. So this is x, its corresponding y value will be f of x. This is x plus h. Its corresponding y value will be f of x plus h. And so the slope of my secant line is just going to be the slope of the straight line that's connecting these 2 points. That's going to be y2 minus y1 over x2 minus x1. That actually leaves me with the difference quotient. But now, in order to turn that secant line into a tangent line, what I want to do is let the distance h approach 0. And so that gives us the fact that the slope of the tangent line can be thought of as the limit as h approaches 0 of this expression. Now this is super important because we actually, believe it or not, I mean, we'll talk about this a little more, because what we just did was solve the rate problem. So this guy is so important, we'll give it a name. This expression, this limit, is a super important limit because it allows us to get to the slope of a tangent line, which is somehow the speed of the line. And because the line approximates a function at a certain point, it is actually the speed of the function in that point, right? And the name that we give this thing is the derivative. So when you talk about what the derivative is a limit. The derivative is the limit of the difference quotient as the denominator approaches 0. So that leads us to the definition. So I'm going to actually officially define this and introduce this guy. So let f of x be a function the derivative of the function f of x at x is given by the limit. And I'm going to introduce a notation here. This is called f prime of x. It's a little apostrophe, kind of a notch. Just write a notch like that. And it's equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Of course, provided it exists, because it's a limit, it's completely possible for it to not exist, and that would simply mean that this function has no derivative at that point. Right? We won't talk about that today, but we will talk about what it means for a derivative to not exist and what it means for a function to be differentiable or not differentiable. But that's basically the idea. Let me talk a little bit more about that notation before we do an example. There are two main notations here. One is called the prime notation. Okay, so that's the notation that I'm using here. So this is when you say f prime of x, or f prime if the x is understood. This is called f prime, or f prime of x. And so basically what that is, it's the derivative of f. So it turns out this limit will give you, if you actually compute it and it exists, it will give you some other function. That function, we will call it f prime. And what that function is, it tells us the derivative of our original function. I'll tell you about how we want to interpret that expression, the derivative. When we hear that, what should we think about? The other kind of notation is the Leibniz notation. So this was a guy who developed calculus independent of Newton. Although these guys were in a feud for many years because Newton accused him of actually copying his work. But that's a whole other thing. So this guy also developed calculus, and he used a different notation. So this was the notation that Newton used. This guy used the notation of that. So here my function is y, and he used the expression dy dx. That's what this is called, dy dx, right? Or you can emphasize it's the derivative of y with respect to x, right? Derivative of y with respect to x, meaning that you're identifying who is your dependent variable and who is your independent variable. So who's on the horizontal axis and the vertical axis? You can write d of whatever that variable is over d of the other variable. That's called dy dx. I'll tend to use this notation in class because it's just easier to write down instead of writing dy dx, just writing f prime or y prime. Right, so that's another way, because if your y is equal to f of x, writing y prime is the same as writing f prime. But this is actually a very functional notation because it looks like a fraction, and in many cases you can actually treat it like a fraction. So for those of you who do have to go on to Calc 2 and maybe even higher mathematics, you'll come up in contexts where you can solve problems by thinking of the derivative notation as literally a fraction that you can move around. So that's the derivative. Interpretation. So not only should you know what a derivative is, but you should know how to interpret it. So when you hear the word derivative, certain things should come to mind, and also it stands to reason if anything over here comes to mind, you should be thinking derivative, vice versa as well. Okay? So derivative is another word for slope. Slope of tangent line. You can also think of it as the slope of the function itself. You can also think of it as giving you a formula to find the slope at any point. You can also think of it as a rate of change. That is at an instantaneous rate of change. You can also think of it how fast f is moving. Right, so you can also think of it as a speed or a rate. Right. So when you think derivative, you can interpret it in any of these ways. And if for some reason you want to find any of these things, you should know that you can do so by finding the derivative. So if I give you some random function and I ask you, how fast is this function changing at this point? You should know, hey, I can use a derivative to figure that out. You know? Or if I ask you, find the slope of the tangent line to this function at this point, you should be using a derivative. Right? Or if I say, hey, find the derivative of this function, how would you interpret that answer? You can interpret it in any of these ways. So let's actually do an example here. We'll only do one, and then we'll do some more later on and talk a little bit more about applications and stuff. Find the derivative of y equals f of x equals x squared. So my function of concern here is the function x squared. At x equals 2, interpret this number. Also find the equation of the tangent line to y equals x squared at x equals 2. So a question like this is one of the most basic questions I can ask about derivative. I'll definitely put a problem like this, similar to this, on the test, on the next test. But it's a very straightforward, it's kind of the main geometrical application of a derivative. So here, our derivative is equal to f prime. So what I really want to find is f prime of this function. And we have a formula for it. It's actually going to be the limit as h approaches 0 of f of x plus h minus f of x all over h. This is the limit as h approaches 0. What is f of x plus h?
X plus h squared.
X plus h all squared minus x squared, which is the original function, all over h. Now things like that we've dealt with many times so far in this semester, so let's just actually move on with this. This will expand, this becomes x squared plus 2xh plus h squared minus x squared all over h. The x squares will kill each other. There's a common h in who remains, so I can factor that out. So now the h's would cancel, and I'm taking the limit as h approaches 0. Since I no longer have h in the denominator because I canceled it, I can now plug in h equals 0. So I plug in 0 here, and so the result will be 2x. So it turns out the derivative of a function, the function x squared, is actually the function 2x. Now how can you think about this expression? What this is, it's a formula for the slope. So it's formula for the slope of the function, or the slope of the tangent line at any part of the function. So for the function y equals x squared, the formula that will give me the slope of that function at any point is the function 2x. But we really care about a specific point at x equals 2. At x equals 2, your f prime of 2 would be equal to 2 times 2. I'm just plugging into this guy, which which is 4. So it turns out the derivative at the point x equals 2 is the number 4. Now how can you interpret that number? This is the slope of the tangent line. Y equals x squared at the point where x equals 2. That's how you can interpret it. We're going to find the equation of this line pretty soon. But if you want to see what's going on, we can have y equals x squared here, doing its thing. We can look at the point where x equals 2. That brings us to here. And if we were to draw a tangent line, like a straight line that passes through that point in such a way that if you zoom in, that line and the function are doing the same thing, such a line will have to have slope 4. If it has some other slope, it's not a good enough line. Because that would mean it would cut through the function and cut it through another point, and it wouldn't behave the same way if you zoomed in. So for a straight line to be approximate that function at that point, it must have slope 4. So that's kind of the picture here. How would you find the equation of the line? Equation of the tangent line. Yeah?
Well, it's linear, so you could use y minus 1, right?
Right, we can use the formulas. A tangent line, don't be fooled, it's just a straight line, so all the formulas that we have for straight lines will apply here. So we can use something like y minus y1 equals mx minus x1, for example. We know so far some things. We know what the m value is. The m in the equation of a line is the slope, and we just figured out what the slope was. It's 4. So we know that m is 4. So because we know the slope of a line, what we need is, we need a point on the line. And since we know that x equals 2, this would mean that our y value is just going to be 2 squared, because the function is x squared. So our y value is 4. And so that means 2 comma 4 is a point on the line. And so now I can actually put these together. So it's going to be y minus 4 equals mx minus 2. And that's the equation of my tangent line. You could also write that as, let's say I want to put it in y equals mx plus b form, which I might not want to, but just in case. That would be 4x minus 8 plus 4. So it's that guy. So it's this or that. So I can have a function y equals x squared, and you can ask the question, well, at the point where x equals 2, if I draw the tangent line to it, what is that equation? Well, this would be the equation of the tangent line, and I can in fact know that the slope of that line has to be 4. That will be the perfect line to approximate the function that will pass through that single point. And again, there are many interpretations we could put on this. Like I can talk about the units of the x and the y. And again, I could think of this as a graph that describes the distance an object is traveling per unit time. So this could be miles and hours. And what this is saying is that at the time 2, this thing is traveling at 4 miles per hour. You could have that interpretation. And there are many other such interpretations, but that's kind of where we'll end for now. We'll do a bunch more examples and talk more about what this all means going on into the future. So remember, we don't have class on Tuesday, so I will see you guys on Friday, and we'll talk a lot more about derivatives.